Okay, this example is referring to the problem of minimum queen to cover the whole chessboard. Okay, suppose we have a chessboard with a given size, a special given size. As you know, chessboards are 8 by 8, but suppose a very special case, it is 4 by 4, and we want to know what is the minimum number of queens required to protect all of the cells. Okay, and these queens should not attack each other. So one of the configuration is shown on this graph. So here you can see that there are 3 queens. This is the minimum number of queens required, and all of the rows are protected. For example, this row, this row and this column are protected by this one. This column and this row is protected by this one, and also you can see here that this guy is protecting this column and this row, and also these 2 cells, and this cell and this cell. Okay, so with 3 queens I have covered all the cells. Okay, but how can we solve this in general mode? So if we are given an n by n chessboard, how many queens are required? What is the minimum number of them required? Okay, so we want to minimize the number of them, so I have to define a binary variable called uij, which is telling us at cell I and j if there is a queen or there is not a queen. Okay, so here this is what we are doing. For every given column j, summation over I should be less than equal to 1. It means that not more than 1 queen can exist on each column, not more than 1 queen can exist in each row, and also on each diagonal the number of queens should be less than 1 or less than equal to 1, so it can be 1 or not, nobody. And also for every for the anti-diagonal cells, the same condition should happen as well. Okay, so let's continue. The last condition, so whatever we talked about is this problem is called minimum queen to cover the chessboard. So in this specific problem we are trying to find out what is the minimum number of queen required for protecting or covering all the cells. Suppose this example is going to be solved for a very special case of chessboard with 4 by 4 dimensions. As we know, usually they have 8 by 8, but this is a special case. So you can see here, by only 3 queens located at this specific location, all of the cells are protected. For example, this cell is being protected by these 2 queens, and no 2 ones are attacking each other. Then we need to define it as an optimization problem if we want to solve it for general case. So we do the summation over I and j, and uij is a binary variable representing the fact that if a queen exists on the cell I and j, and also for every given column like j, if we do the summation over the rows, then there will be not more than 1 queen on each column, and also there will be not more than 1 queen on each row, on each anti-diagonal, and on each diagonal rows of cells. Okay, and so these 4 conditions are designed for queens not to attack each other. And also we need another one. Okay, so if we just use these 4, then the obvious solution to this problem will be no queen at all. Okay, so we need another kind of constraint saying that for every I and j, if we do the summation over UC and R. Then for every diagonal or anti-diagonal, or every row or every column passing through that cell, the summation should be bigger than or equal to 1. Okay, so it means that it should be protected by at least one queen. Okay, so if we solve that, we can see the results for the 4x4 case. So if n is 4, then the solution is that. And also we can test it for a bigger chessboard, 6x6 or 8x8, the traditional one. So the 8x8 chessboard can be protected by only 5 queens. And if we make it bigger, let's make it 10, then it can be protected by 6 queens. Okay, so I'll show you the Python code for solving this specific optimization problem, which is a linear programming, Mixingen linear programming. As usual, we import the required packages. N is representing the size and dimension of the chessboard. I is representing the queens, different queens, and J is the alias of I. U is a binary variable defined over I and J. So we need to define some rules for not attacking to each other. So these 3 rules are designed in order to the first one, let's have a look at this one first. So the first one is telling us that each cell I and J should be protected by at least one of these conditions. So there should be a queen on the diagonal or anti-diagonal, or I is equal to R, or J is equal to C, or from the same row, from the same column, or from the diagonal or anti-diagonal. And also the remaining ones are designed in order to not, the queen do not attack each other, as I explained. And the objective function is the summation over uij for every I in model I and for every j in model j. The solver is chosen to be GLPK because it's linear integer programming. And then we provide the model to the instance creation. The instance will be created and the results are obtained after the solve. And finally, the solutions are graphically shown here. Okay, and finally it can be saved somewhere on your machine as a gmin n queen.png, for example. Okay, so I run the code for you. It is running now. So for simplicity, we have assumed that n is changing between 4, 6, 8, and 10. You can change that number as well. Okay. I hope you learned something useful in this lecture. Thank you very much.